Transmission lines, line transients, series on transmission line theory, lecture number 2.40. This is first session on line transients. In this session, the focus is mainly on lines response for a step function excitation. Transmission lines are mainly used for the purpose of transferring signal, carrying signal from one point to another point. The signal may be analog or it may be in digital form. So far, we concentrated on the line, its behavior when it is carrying an analog signal. Now we turn our attention, we turn our focus to estimate the response or behavior of the line when the digital signal is put over it for transmission. Digital signals mostly they take the form of rectangular pulses. Each one of the rectangular pulses can be considered, can be viewed as a combination of two step functions of opposite polarity. Now, if our requirement is to know the behavior of the line when it is put to use to carry digital signals, then it is just sufficient to know its behavior or its response for a step function excitation. The reason is the response of the line, behavior of the line for step function excitation can be extended. To find the response of the line for the rectangular pulse excitation using linearity property or superposition principle. Behavior of the line for pulse excitation is behavior of the line for digital signal transmission, because digital signals most of the times they take the form of rectangular pulses. Hence, line response to a step function is key to know the response of the line for digital signal transmission. In the present session, we focus on line terminated over matched load, mismatched load, terminated over a capacitor, terminated over inductor, and try to estimate its response for a step function input. Here we also consider ideal source conditions and also non-ideal source conditions. When I say ideal source conditions, I mean the source with the zero internal resistance. When I say non-ideal conditions, I mean source with the non-zero internal resistance. Both type of sources we consider. Now let us move further to investigate the behavior of line under step input conditions. Let us start with a few introductory points on line response for a voltage step. The responses of line to voltage step and pulse functions are examined in the present session. The study of line with these inputs helps us to understand behavior of line when it is used for digital signal transmission. It is also useful in understanding the line functioning, in storing and releasing energy in pulse formation applications. In the present session, the attention is confined to lossless lines, which are assumed non-dispersive, even though in reality, as voltage steps and pulses are composed of several frequency components, dispersion takes place inevitably. So it is an assumption, somewhat unreal, that the lines are non-dispersive in the present discussion. Pulses get broadened with the propagation distance, and their shapes may also change when the load is complex. Now, the response of a line for a step voltage input terminated by a matched load first and then by a mismatched load is considered. The line terminated over reactive elements like inductor, capacitor is considered. When termination is mismatched, the incident wave produces a reflected wave of the same dependence, time dependence. That is, reflected waveform is same as incident waveform. In mismatched case, using a constant value reflection quotient, the transient behavior can be analyzed. When termination is reactive element, the reflected wave no longer shows the same dependence as incident wave, and a constant reflection quotient is no longer useful for analysis. A differential equation governing the voltage current or the termination is used to find transient response, transient performance. So when the termination is resistance, then reflection quotient. It is useful for the analysis, but when termination is inductor or capacitor, it is no more useful. You have to go for a differential equation which governs voltage and current over the termination for finding the performance of the line. To begin with, analytical means of finding the response is undertaken, and then a graphical aid called reflection diagram is introduced to investigate the voltage and current profiles over a mismatched line with respect to time. We undertake the analysis with reflection diagrams in the second part on line transients. Here is shown a line, lossless line, terminated over a resistor load. In A, in B, same line, termination is slightly different. In A and B also, termination is a resistor in both the cases, but in A, it is matched termination. In B, it is mismatched termination. Matched termination means load impedance is equal to characteristic impedance of the line. As the line is lossless, Characteristic impedance of the line is pure real quantity, purely resistive. Characteristic resistance. So in case A, terminating resistance is equal to characteristic resistance of the line. In B, terminating resistance is different from characteristic resistance of the line. A voltage source with some internal resistance, it gets connected to the line when switch S is closed. When switch is closed, suddenly an amount of voltage equal to V0, a step voltage, it gets connected to the line, and a voltage wave, forward wave, and also a current wave, forward wave, it starts traveling with certain amount of velocity. As the line is lossless, that velocity is 1 by square root of mu epsilon. Or in terms of primary constants of the line, it becomes square root of LC. This step then reaches the load point after some time. As the termination is matched one, this step gets absorbed without any reflections. In case of termination not matched to the line, which is depicted in B, a part of the incident wave over RL, it gets reflected, initiating another wave. It is also a step function. This wave then starts traveling towards the source. Now over the line there exist two waves, a forward wave, a reverse wave. Some more detailed description regarding the analysis of line when terminated with matched load, when terminated with mismatched load. Both the cases. They are discussed right now in the next slides. Now matched load. Let us suppose Rg is 0 and RL equal to R0. Rg is internal resistance or impedance of the source. First we consider Rg equal to 0. Then the voltage wave of amplitude V0. V0 is voltage of the source, and an associated current wave of amplitude V0 by Z0 start traveling. When they fall over the load at a time T equal to L by V. L is length of the line, V is velocity of the wave. As the termination is matched, no reflection occurs there. After this incident, the voltage and currents at any point over the line remain same and are V0 and V0 by Z0 respectively. When Rg is different from 0, internal resistance of the source is non-zero, then what happens? Voltage division takes place at source end between source and line impedances, resulting in voltage and current waves V plus and V plus by Z0 respectively over the line, where V plus is V0, R0, Rg, R0. This is V plus. When Rg equal to 0, it is V0. When it is non-zero, it is V plus. Except that everything is same. Now we consider the situation, mismatched load situation. Let us suppose RL is different from R0 and Rg is different from 0. Reflections from load and source keep on producing waves over the line, and the total voltage at any point over the line is sum of voltages of all the waves crossing that point. So multiple reflections over the line, multiple reflections, one step wave, one step function. From this another step function. Keep on moving from this side to that side, that side. It is a case of multiple reflections over the line. This situation can be analyzed. The load voltage in terms of RC over the load and source is, in this case, it is denoted by VL. VL is V1 plus 1 plus gamma L. Gamma stands for reflection quotient. Gamma L stands for reflection quotient over the load, divided by 1 minus gamma G gamma L. Gamma G stands for reflection quotient over the generator. A little bit of analysis, a few steps. They give us this particular expression. Here V1 plus is V0 R0 by Rg plus R0, voltage division at the input side. Gamma L is RL minus R0 by RL plus R0. Gamma G is Rg minus R0 by Rg plus R0. These are standard expressions for reflection coefficient. Whereas this thing happens because Rg is not 0. Note that in case of Rg equal to 0, the Rc at the source and gamma G is equal to -1 and V1 plus equal to V0. The basic point one has to keep in mind is when termination is over a mismatched load, there is a possibility of multiple reflections. Of course, when the source is matched with the mismatched load, there exists reflection only once at the load. If line is mismatched at both the ends, it leads to infinite number of reflections, multiple reflections, never ending reflections. Ultimately, the load voltage, it becomes equal to the expression V1 plus multiplied by 1 plus gamma L by 1 minus gamma G gamma L. Now we consider inductor load. Earlier it is resistance, now inductor. Next we consider capacitor. Here certain governing relations, governing equations, they are given. VL of t plus R naught IL of t equal to 2 V1 plus. When t, here t stands for time, t is more than capital T. Small t stands for time variable, whereas capital T stands for time required for the wave to reach load point from source point. Of course, VL of t is LL DILT by dt. This is a voltage current relation across inductor. Combining these two gives us a differential equation. Solving this differential equation, we get an expression for current. Once current expression is available, voltage across the inductor can be found using V equal to L di by dt. This expression gives us V1 minus of t is equal to VL of t minus V1 plus. Ultimately, it gives us 2 V1 plus e power minus t minus capital T multiplied by R0 by LL minus half. At a point x equal to x1 over the charged line, the voltage is V1 plus before reflected wave crosses the point, and it is V1 plus plus V1 minus T minus capital T after reflected wave passes over that point. Voltage distribution along the line for T1 in between capital T and 2T is shown in the figure. See, this is the step function that is traveling towards the source. This step is falling exponentially towards low values. Next, we consider capacitor termination. I equal to C dV by dt. This is voltage current relation between voltage and current pertaining to a capacitor. And the governing relation, differential equation as far as circuit is concerned is given by the second equation, CL dVL of t by dt plus 1 by R0 VL of t equal to 2 by R0 V1 plus. This equation is for t more than or equal to capital T. Combining these two, we get another equation which can be solved for voltage and also current. An expression can be obtained for voltage. It appears like V1 minus of t equal to 2 V1 plus multiplied by half minus e power minus t minus capital T by R0 CL. The voltage at an arbitrary point x equal to x1 over the charged line is V1 plus before the reflected wave crosses the point, and it is V1 plus plus V1 minus t minus t after the reflected wave passing over that point. Voltage distribution along the line when T1 is in between T and 2T is shown in the figure. Here, an exponential rise is moving towards the source. Exponential rise from 0. In case of inductor load, it is fall, exponential fall, that is moving towards the source. This is what I have to share with you. I want to share with you for right now. To recap, in the present session, we considered the line with different terminating conditions like match termination, mismatch termination, inductor termination, capacitor termination, and also with ideal source and also non-ideal source to find its response for a step input function. Hope you have enjoyed this session. Also hope you learned good amount of subject in this session. Enough for now. Hope we meet again soon in another session. Bye bye.